Look at the scale of these data centers. Tech giants are racing to pack unprecedented computing power into massive server racks, just like these. Yet the most advanced supercomputers on Earth are currently bottlenecked by one of the cheapest, most common materials on the planet, plastic. If you zoom in past the servers and look directly at the hardware, you'll notice a green circuit board beneath the dark silicon chip. That metal layer is called the substrate, and it is the essential physical base that connects the silicon die to the larger computer. This diagram shows exactly how that substrate functions. It acts as a translator. The silicon brain on top has ultra-dense microscopic connections, and the substrate takes those tiny pathways and spreads them out so they can physically plug in to the larger motherboard below. To handle massive AI workloads, engineers are grouping multiple, highly demanding chips side by side on a single package. Pushing enormous amounts of power through this configuration generates intense localized heat. Traditional substrates are made of organic plastic resins mixed with fiberglass. When you subject that plastic foundation to extreme temperatures, the material inevitably expands and warps. In engineering, if a foundation bends even a fraction of a millimeter, the microscopic connections between the chip and the board are physically torn apart. The pathways snap, and the hardware instantly dies. The semiconductor industry has reached the physical limit of what organic plastic can endure. If the physical foundation isn't replaced, the hardware powering artificial intelligence will quite literally melt its own infrastructure. To bypass this bottleneck, the entire supply chain is ripping up the playbook. They are turning to highly engineered advanced borosilicate glass to serve as the new core substrate. Unlike plastic, glass offers absolute thermal stability. It is entirely rigid and barely expands when baked, keeping the chips perfectly secure, even under the immense power loads required by AI workloads. Look at this microscopic cross-section. On the left, organic plastic is uneven, like a mountain range. On the right, glass is flawlessly smooth. This perfect flatness allows engineers to print wires much closer together. While plastic supports few connections, glass densely packs interconnects side by side, achieving 10 times the wiring density. While glass effectively solves the heat problem, its real value is the pristine, high-density canvas it provides for chip architectures that were previously physically impossible. The third major technical advantage of this material relies on something called through-glass vias, or TGVs. As we see in this diagram, engineers use high-precision lasers to drill millions of microscopic holes straight through the solid glass. They then fill those holes with copper, allowing data and electrical power to travel vertically through the substrate with almost zero signal loss. If glass is so superior, the question is why we haven't used it until now. The answer lies in the precision required to drill millions of tiny holes into thin glass, a capability that only recently moved from the lab to the factory floor. Raw glass is notoriously fragile. Any slight miscalculation in laser pressure or robotic handling instantly shatters the entire substrate, destroying the product. The industry has moved past the theoretical material science. Now the challenge lies in the logistical difficulty of manufacturing these fragile glass cores at a global scale without catastrophic breakage. Because the plastic bottleneck poses a severe physical limit, companies have launched a multi-billion-dollar research and development race to make glass chip manufacturing a reality. Intel has invested heavily in R&D to pioneer these techniques, licensing patents to accelerate the market. Meanwhile, TSMC, the foundry that builds the physical chips for companies like NVIDIA, is rapidly scaling up their own glass production lines to meet the impending demand. This requires spinning up an entirely new global supply chain. Chip makers are now relying on optics companies like Corning and Schott to manufacture the highly engineered glass panels needed to feed these fabrication plants. If they can successfully scale this manufacturing process, silicon chips can continue growing in physical size, density, and processing speed without melting under their own power. Standard consumer electronics will stick with cheap plastic for the foreseeable future, but the absolute bleeding edge of human computation, the infrastructure powering the AI revolution, will be permanently built on a foundation of glass.